Okay, hello and welcome back. We're going to continue our introduction to the local theory of surfaces. And here in this part, I would like to concentrate on examples. So was our setting, let's recall that our settings, we have some immersion from a two-dimensional surface into R3. And we defined the metric by the metric is each point is a 2x2 symmetric matrix, and the coefficients of this matrix are given by the inner products of partial derivatives. We also defined the second fundamental form. So you can compute the second fundamental form by taking the inner product of the normal with the second derivative, the corresponding second derivative of the immersion. These are all inner products with respect to Euclidean space. And this ends up being the same thing as minus the inner product of dI n with dj psi. Okay, so the example I want to start with, this is really going to be a class of examples, is that of a surface of rotation. So the picture you have here is we have some profile curve where the distance, so this profile curve here lives in the YZ plane. And the distance from this curve to the z-axis is given by rho. And I obtain the surface by rotating this profile curve about the z-axis. And once I do that, I obtain the mapping capital psi from a cylinder. So this is now a cylinder. I have a mapping from a cylinder into R3 given by this formula. So I can compute some derivatives. I can also compute my normal by taking a cross product. So I'm going to take pt psi crossed with d theta psi. And when I do that, I'm going to obtain minus rho dot cosine theta minus rho dot sine theta. And the last term I get will be rho times rho dot. Oh, sorry, I don't have any rho dot here. Let's rewrite this. This cross product is going to be minus rho dot. Minus rho cosine theta minus rho sine theta rho dot. So if I compute the normal, which is going to be this cross product divided by its length, I'll find this vector 1 over square root 1 plus rho dot squared minus cosine theta minus sine theta rho dot. And I'd like to observe that this is an inward pointing normal. And this geometrically makes sense if I go back up to my picture, I see that the normal will point in. If I go around one of these meridian curves, I would like these meridian curves to have positive curvature in some sense. And I see that tracing around these meridian curves, the curve itself will bend towards the normal vector. And that is the appropriate sense in which that's the appropriate sense in which the curvature of that curve should be positive. Okay. I can compute the metric in these coordinates, the metric induced. When I compute the induced metric, the first term I get is 1 plus rho dot squared. The cross term is 0. These component directions are already orthogonal, so that's kind of convenient. And the last term, the d theta term, that term is rho squared. Right. It would be convenient for some later computations to record that the inverse matrix has this form. Okay, so carrying on, we compute some more derivatives. So second derivative gives you have rho double dot cosine theta, rho double dot sine theta, 0. T theta gives you minus rho dot sine theta, rho dot cos theta, 0. And finally, the pure second derivative with respect to theta gives you minus rho cos theta minus rho sine theta, 0. So when I take inner products with the normal vector for the TT term, I obtain so I'm going to have this prefactor of 1 over square root 1 plus rho dot squared. And then I have then I'm going to have minus rho double dot. And again, the second polynomial form is diagonal. The cross term is 0. Sorry, the term with mixed derivatives is 0. So I conclude that Hij is going to be, I'll have a prefactor of 1 over square root 1 plus rho dot squared. This term is going to be minus rho double dots. There, and then rho. We'll also need to write down this. So now we see that the principal curvatures on the one hand, I'm going to have one principal curvature, which looks like rho minus rho double dot over 1 plus rho dot squared to the 3 halves. And the second one I'm going to have as 1 over rho square root 1 plus rho dot squared. The Gauss curvature is the product of the two principal curvatures. And I see right from here that the sign of the Gauss curvature is given by rho double dot. And finally, the mean curvature is 1/2 the average. So if I have a minimal surface, it will satisfy that the mean curvature equals 0. And this gives us the ODE. I'm going to write the ODE in the following way. I want it to be 1/2 plus rho dot squared to the minus 3/2. And then I'm going to have a minus rho double dot plus 1/rho times 1 plus rho dot squared. And I can equivalently write this as rho double dot is equal to 1/rho 1 plus rho dot squared. Now I have a relatively nice looking ODE for a surface, for a minimal surface of revolution. And we can actually write down all of the solutions of this ODE. And we're going to start with the one we might know. We're going to start with the one that reads rho of t is cosh t. So you may have learned at some point about the catenary. And if I rotate the catenary, I obtain a minimal surface. And this is a solution. Right, so I see from, so I can check that I'm satisfying the correct ODE. Rho double dot is indeed cosh t. 1 plus rho dot squared is 1 plus sinh squared t, but that's equal to cosh squared t. So 1/rho times 1 plus rho dot squared is indeed cosh t. So I'm satisfying the correct ODE. And now what can I do? Well, I can rescale and translate in the time variable, in the variable t. And now I see by choosing the parameter A and capital T correctly, I can match any initial condition for my second order ODE that I please. Let's write it this way: rho of 0 is equal to alpha and rho dot of 0 is equal to beta. Right, so I can solve for any alpha, beta, real numbers. I can solve my initial value problem for any choice of my initial values. And that tells me now that I've found all the solutions to the appropriate ODE, and this actually gives you all of the rotationally invariant minimal surfaces, with the exception of one very important example, which is sort of the example you get in the singular limit when you let A goes to 0. We also have the singular limit when A goes to 0 from above, and this gives the flat plane, which is of course a minimal surface and also a surface of rotation. Okay. Right. One more example here within the realm of surfaces of revolution. Let's look at another. So let's look at another pair of surfaces, So another also. If we take rho identically equal to 1/2, what do I obtain geometrically? I obtain a right circular cylinder centered on the z-axis with radius 1/2. And what do I see? I see in this case that kappa 1 is 0, kappa 2 is 2, so h is 1/2 2 plus 0, which is 1. K is 0. So this is an example where you see the cylinder is intrinsically flat. So it's flat. And it has mean curvature So this is the ambient induced curvature equal to 1. The other surface you know with mean curvature equal to 1 is, of course, the sphere. So let's check what we get for the sphere. In the sphere, we have rho of t is square root 1 minus t squared. Minus 1 less than t less than 1. We see that rho dot in this case is minus t times 1 minus t squared to the minus 1/2. And 1 plus rho dot squared is 1 plus t squared over 1 minus t squared, which ends up just being 1 minus t squared plus t squared over 1 minus t squared. Right. If I carry on and compute a little bit more, so I'll see that, for instance, cap 2 was 1 over rho square root 1 minus rho dot 1 plus rho dot squared. So I get one term which looks like 1 over square root 1 minus t squared. And I have another term that looks like 1 over square root 1 over 1 plus rho dot squared. And that's equal to 1. Kappa 2. So right, to compute the other principal curvature, I'll need to compute rho double dot. And for this, I'll need to take a derivative one more time of this guy up here. I get one term from differentiating the t. I'm going to get another term minus is minus t squared. It's t squared to the minus 3/2. And it might be convenient to pull out the common factor of minus 1 minus t squared to the minus 3/2. And what do I have left over? I'm going to have one term that looks like 1 minus t squared plus another factor of t squared from this term here. And so all I'm left with is minus 1 minus t squared to the minus 3/2. So then if I plug that in, I'll see that minus, which is kappa 1, is minus rho double dot over 1 plus rho dot squared to the 3/2 is going to be, so on the top, I'm going to get 1 minus t squared to the minus 3/2, but on the bottom, I'm also get 1 minus t squared to the minus 3/2, which ends up being 1. So I see that in this case, for this parameterization of the sphere, I see that both of my principal curvatures are equal to 1. And I see that, again, my mean curvature is equal to 1. And my Gauss curvature is also equal to 1. Okay, so these are good examples to have in your head. I want to also discuss the case of graphs. Sometimes you'll see this referred to as the non-parametric setting for surface theory or for minimal surfaces. So in this case, I want to parameterize my surface this way. I see that the derivative of the parameterization with respect to u is going to be 1, 0 df du. The derivative with respect to v is going to be 0, 1 df dv. The metric will have the form 1 plus df du squared and 1 plus df dv squared along the diagonal, and the off diagonal term will be, of course, well, let's write it this way as f sub u times f sub v. So here I'm letting the subscript denote the partial derivatives. So again, I can invert this. I see that the determinant of this matrix is 1 plus the length of the gradient squared. So I can write the inverse matrix as 1 over this 1 over 1 plus the length of the gradient squared. And then I'm going to have a 1 plus fv squared here minus fu fv minus fu fv and 1 plus fu squared. When I take more derivatives, so the first thing I see is that the second derivatives are going to be 0, 0 fuu. The next one's going to be 0, 0 fuv. And the last one is going to be this term. Let's go ahead and compute the normal derivative, the normal vector. So the first term I get is going to be minus FU minus FV 1. And when I divide by the length of this normal, I'm going to get 1 over square root of 1 plus the length of the gradient squared minus FU minus FV 1. And again, I have a downward pointing normal. So when I write out the second fundamental form, I'll find this guy. Which is essentially the Hessian of F, but I have to multiply by this prefactor. When I multiply by the inverse of the metric, I'm going to get, this time I have a prefactor of 1 plus the length of the gradient squared to the minus 3/2. And now I'm going to get 1 plus FV squared minus FU FV minus FU FV 1 plus FV FU squared. And then I'm multiplying by this Hessian matrix. And what do I find? So let's see. I'm going to have an FUU times 1 plus FV squared. Minus twice FU FV FUV plus FVV 1 plus FU squared. sorry, this is not what I want. Let's see. Okay, I keep this prefactor. And then the first term I have is going to be FUU times 1 plus FV squared minus FUV, FUFV. The next term I get is going to be the next term I get is going to be FUV times 1 plus FV squared minus FVV FUFV. I'm going to have a term that looks like FUV times 1 plus F U squared minus FUU FUFV. And the last term I get is going to be the last term I get is going to be FVV times 1 plus FU squared minus FUV FUFV. So if I take the trace of this, what are all the terms I'm going to get? I'm going to get an FUU times 1 plus FV squared plus an FVV times 1 plus FU squared. And then the last terms reinforce each other. This term is the same as this term, minus twice FU, FV, FUV. If I want to set this equal to 0, I'll obtain, if I want to set this equal to 0, I will obtain the minimal surface equation. And this is the PDE a minimal graph must satisfy. I have the equation FUU times 1 plus FV squared plus FVV times 1 plus FU squared minus 2 FU FV FUV all equals 0. If I do a little bit of work, I will see this is equivalent to saying that the divergence of gradient f over plus length gradient f squared equals 0. So this is an equivalent. This is usually called the weak formulation. That's an equivalent condition. Right, so this is now a nice PDE for minimal graphs. This is if I have a graph which is a minimal surface, that graph must satisfy this partial differential equation. Okay, we're going to stop there for now, and we will continue in the next video.